The best way to understand a polynomial inequality is to first look at a solution that's found from the graph. In this case, we're going to look at a cubic polynomial in an inequality where the polynomial is set greater than or equal to 0. And we're looking at a graph of this cubic polynomial. So I'm going to consider that 0 to be y equals 0, which is the same as the x-axis. And because my inequality is a greater than, it's a greater than or equal to, but for the purposes of figuring out the direction, I'm just considering the greater than. I am going to interpret that as the word above. So my first task is to highlight the portion of the graph that is above the x-axis. That would be this portion and this portion. Now this is a polynomial graph, so even though there aren't arrows drawn on it, I know that it does keep going off to infinity here in the right direction. So I'll go ahead and put an arrow on my highlighted portion of the graph. To get my solution set, I need to express this in terms of the input variable x. So I notice that it starts here at -3, it goes up to -1, and it starts over again at 2, and even though this arrow looks like it's pointing mostly up, I know that it is also going to the right, and therefore this interval is going to go to the right all the way to positive infinity. So my solution set, now I'll consider the fact that this is greater than or equal to rather than just strictly greater than, and that tells me that my endpoints are all included here where it's equal to 0, so that my solution set starts at -3, goes up to -1 using square brackets, then I'll put a U for a union symbol, starts over again at +2 and goes to positive infinity, with only a round parenthesis at infinity because we never include infinity in our interval. To best understand the process of solving without a graph, we generally use a number line. We can see that the information we really needed from this graph are: 1, where does the graph cross the x-axis? It crosses at -3. It crosses at -1, and it crosses again at +2. And the second piece of information we need is: where is the graph above the x-axis and where is it below? We can see that to the left of -3, this region over here, the graph is below the x-axis. That corresponds to negative y values, so I'm going to mark this interval with a negative. Between -3 and -1, it is above, which corresponds to positive y values. Then it drops below again, and to the right of 2, it is above. So we could, based just on this number line, identify the intervals over which the function is positive and negative. Now, to figure out whether I want the positive or the negative intervals in my solution, I need to look back at my original inequality. That inequality is greater than or equal to 0, so we called that above the x-axis, but we could also call it positive. Numbers that are greater than 0 are positive numbers. So looking at this number line, I would know from the inequality to highlight the positive intervals. And then to consider whether it's a strict or an inclusive inequality to determine my bracket type. So from this number line also, I would be able to get my solution set that I have written down here from the graph. This is the process we're going to follow when solving symbolically. We call these numbers that make up the endpoints of our intervals boundary numbers. The boundary numbers are just the zeros of the polynomial because, as we saw from the graph, they're the x-intercepts of the polynomial graph. So our process is to mark the boundary numbers on a number line and then to test the intervals. And we will talk more about how to do this part. This is the only part that we haven't seen yet, right? We'll talk more about how to do this part as we get into this next example. So I'm going to need a number line for this, and I'm going to mark on this number line what the zeros are of the polynomial. Now, looking at this polynomial here, the first thing I want to do is get all the terms on one side. 2x cubed minus x squared minus 3x is less than or equal to 0. This is the polynomial that I'm going to refer to anytime I'm working with the number line. To find the zeros, in this case, I'm going to try factoring. Factoring won't always work, but if it does work, it's usually the easiest approach. So I'll factor in x out of the whole thing. And then I'll try factoring by trial and error, starting with a 2x and an x in order to get that first term of 2x squared. So I know I want a 3 and a 1 here. I'm not going to put the 3 in the second factor because I don't want it multiplied by the 2x for that middle term. So I'm going to guess that I want this 3 negative and the other term positive. I do a quick check on the middle term and see that 2x times 1 is my outer term. Negative 3 times x is my inner term. So that gets me the minus x that I want to have as my middle term. So this is a correct factorization. Now I'll set each factor equal to 0 to find the zeros of the polynomial. X equals 0. If I set 2x minus 3 equal to 0, that gives me x equals 3 over 2. And if I set x plus 1 equal to 0, that gets me x equals negative 1. I am using equals here, not less than or equal to. That's a very important point. All three of these need to be equals. We are finding the boundary numbers. We are not yet finding the solutions to the inequality. I'm going to now mark the boundary numbers here on this number line. Negative 1 is the furthest to the left, 0 is in the middle, 3/2 is on the right. I am not concerned about scale, nor do I want to mark any numbers on here that are not boundary numbers. Marking any numbers on here other than these three numbers might just make it more confusing, right? I want to know each of these is a boundary number. That means that the graph is going to change from positive to negative or negative to positive as it crosses these numbers. It cannot change sign anywhere but these numbers. So the next thing I need to do is test the intervals. That later that we promised is now. We're going to test these intervals on the polynomial. There are lots of different ways to do this. For most of these ways, it's helpful to start by picking a representative value from each interval. Notice these are not the boundary numbers themselves. These are numbers that are in the interval. So I want a number that's to the left of negative 1. I'm going to choose negative 2. I want a number that is between negative 1 and 0. I'm going to choose negative 1/2. I also want a number that's between 0 and 3/2. I'll choose positive 1. And I want a number that's to the right of positive 3/2. I'll choose positive 2. So lots of different numbers could work for this. These are the ones I'm choosing. I usually pick the simplest number from each interval. I picked negative 1/2 only because there are no integers between negative 1 and 0. So I'm going to make up a table and analyze the sign of this polynomial at each of these values. Here in this table, what I have set up is, first of all, a column for x. That's where I'm going to put these representative numbers that I came up with. So there's one number from each interval. In the middle, I have all three factors, so I'm going to figure out the sign of each factor. On the right, I'm going to figure out the sign of the product of all three factors. So first, the factor x, when x is equal to -2, is negative. The factor 2x minus 3, when x is equal to -2, is negative. Specifically, it's -7, but I don't care what the number is. If I can tell it's negative, that's all I need to write down. The factor x plus 1, when x is -2, is -1, meaning it's also negative. Now over here on the right, I'm going to put it all together. This is a product of three negative numbers. Because 3 is odd, I know the product of an odd number of negatives is going to be negative. So I can do this for each of these values. I'll go a little faster. If x is -1/2, x is negative. The second factor is negative. The third factor is positive because the -1/2 is a little bit smaller than 1. This is a product of two negatives where 2 is even, so that's going to be positive. I don't care how many positive numbers are multiplied here. I'm just counting up the number of negative factors, and if I have an even number of negative factors, then I know that the sign of the whole polynomial has got to be positive. If x is 1, that first factor is positive. The middle factor is still negative. The third factor is positive for a negative product overall. And if x is equal to 2, I have positive, positive, positive for a positive overall product. So now I'm going to transfer these signs over to my number line. First, looking at -2, I can see I came up with a sign of negative, so I'm going to put negative in this first interval. I can see that they alternate signs each time. So I'll go ahead and follow that pattern and alternate signs each time. Now, to figure out which intervals are in my solution set, I come back to this inequality here, which uses the same polynomial that I used to figure out the signs. That's important. That polynomial didn't change at all. It just got factored. And I'm going to look at what this is saying relative to 0. Less than 0, numbers that are less than 0 are negative. That tells me that the intervals I want to include in my solution set are the ones in which the value is negative. So this has an implied arrow. This here is negative. Now I can consider the bracket type. This is again an inclusive inequality. So at all of these zeros, I am going to have square brackets. And now I'm ready to go ahead and write my solution set down here. Starts at -infinity, goes up to -1, starts again at 0, goes up to 3/2. And that is it. We will look at a couple more examples just to make sure that we have the idea and that we've seen some of the other patterns that can show up. This next example is a little bit easier by virtue of the fact that it is given to us already in factored form. If it's given to us already in factored form and we have 0 on the other side, this is a gift. We do not multiply it out. We want these factors. We're going to start by just finding our boundary numbers and marking them on a number line. This first one gives us x equals 2. The fact that the factor is squared is going to affect my final answer, but it doesn't affect my boundary numbers. That's just two factors of x equals 2. Each of them give me the same boundary number of 2. The second factor gives me x equals -5. And I can now go ahead and set up my number line. and mark these two numbers, always starting with the smaller number and going up to the greater number. All right, so next we need to figure out the sign pattern here. The fact that the first factor is squared actually makes this a little bit easier. Thinking about our sign patterns, in the last example, we set up a sign for each factor, but notice a squared factor can't be negative, right? This is always positive. The only place where it's 0 is at that boundary number x equals 2. So everywhere other than 2, so at any value that I could possibly pull off this interval, that factor is going to be positive. That means it's not going to affect my sign pattern at all, and the x plus 5 completely determines the sign pattern. So that's going to make it go quicker when I fill in the signs here. I will still pull representative numbers from each interval. So I want something to the left of -5, I'll take -6. I want something between -5 and 2, I'll take 0. And I want something to the right of 2, I'll take 3. Plugging in -6 to x plus 5, I get -1. That tells me that this whole polynomial must be negative on this first interval. Plugging in 0 for x in x plus 5, that gives me 0 plus 5, which is 5, which is positive. That means this whole middle interval, the polynomial must be positive. Plugging in 3 for x in x plus 5 gives me 8, which is positive, so that tells me this whole interval is also positive. It's not a coincidence that the factor that's always positive, this x plus 2 squared, right? The boundary number that came from it, we don't see a sign change as we go across that boundary number. That's because the polynomial is equal to 0 here, but it really doesn't cross. The graph doesn't cross. This is a 0 of multiplicity 2. The graph turns back around again, and the polynomial stays positive on both sides of this number. So I am now ready to figure out which intervals are part of my solution. And for that, I'm going to look back at the inequality in its original state. This says greater than 0. Numbers that are greater than 0 are positive. And because of that, the intervals that I want to select here are the ones in which the polynomial is positive. So here's one, here's another. I'm not going to just run right over that 2 until I've thought about it a little bit. It really depends on what kind of inequality I have, whether it's strict or inclusive. In this case, the polynomial is strict. I only want the values for which the polynomial itself is strictly greater than 0. At x equals 2, the polynomial is equal to 0. So because I would use round parentheses for a strict inequality, I am going to have to exclude 2 from my solution set. If this had been an inclusive inequality, I could just run right over the 2. It would be included in my solution set. But because the inequality is strict, and the polynomial is equal to 0 right there at x equals 2, I have to separate this out as 2 disjoint intervals. So we'll go from -5 to 2, put in a union, start over again at that same 2, and go up to positive infinity. Now we'll look at the next inequality, which is quadratic. These quadratic inequalities are a little bit simpler because their graphs are always parabolas, so we can use a little bit of information we already have about the graph of these to help us fill in that sign pattern. What makes this one a little bit trickier is that we're not going to be able to find those zeros by factoring. So the first process of finding those boundary numbers is going to be a little bit more removed from the rest of the problem. Still, I'm going to start by getting this inequality into a form that has 0 on one side. So I will write this as minus x squared plus 7 is less than 0. And this is the inequality that I will refer to when I get to the stage of marking up a number line and determining my solutions. So this is my main inequality. For finding the zeros, I can't factor it, so I have to just change this less than temporarily into an equals and come up with some other way of finding those boundary numbers. I'm going to call this minus x squared plus 7 equals 0. I'm going to add x squared to both sides. I could just as easily accomplish this by subtracting 7 from both sides, but then I would still have to deal with the factor of -1 later. This moves the x squared over to the right. And then I'm ready to solve it by the square root method. Taking the square root of both sides, I have to use a plus or minus on the side with the number. That gives me that plus or minus the square root of 7 is equal to x. So I can now mark up a number line, putting negative square root of 7 on the left and positive square root of 7 on the right. And I can look at, again, I want to go back to this form of the inequality for everything. I need to look at this for marking up the number line and for determining the solution region, right? I can't look at two different forms because there's some danger that they won't be consistent with one another. This is a parabola that opens down. So I can just use that information to mark up these intervals. If it opens down, it has to go minus, plus, minus. Now, from the fact that it's less than 0, that tells me that the numbers I want are negative. So I'm going to choose solution regions in which the whole polynomial is negative. It looks like I have these outer two lines here. And now, finally, I'm going to think about the bracket type. It's a strict inequality, so these have got to be parentheses. And I will go ahead now and write my solution set as starting from -infinity, going up to negative square root of 7, starting again at positive square root of 7, and going up to infinity. If you didn't want to use the knowledge of this being a parabola and wanted to take representative numbers from each interval instead of the way I just did it, which is kind of a shortcut, that would also work. Let me just show you real quick what that would look like. I could pick representative numbers from each interval, like -3, which is smaller than negative square root of 7, 0, which is between the two, and +3, which is greater than square root of 7, -3, 0, 3. But since I don't have a factored form, I would have to just plug them in directly. So if I plug -3 in for x, this gives me -9 plus 7, which is -2. If I plug in 0, I get 7. And if I plug in +3, I again get -2. So that also would give me this sign pattern of negative, positive, negative, which I could use to mark up my number line, and everything after that would go the same way that it went with me marking up the number line instead from the shape of the parabola. So if you're not able to factor the expression, you can still figure out your sign pattern by using representative numbers. You'll just have to plug them into the whole expression and evaluate it instead of plugging them into each factor and doing that quick sign analysis that doesn't involve coming up with a number.